Some of you aren't. Some of you are better people than I am. But if you are anything like me, you were pretty tired yesterday because you screwed up your sleep schedule over break and you weren't really prepared coming in. And you just probably, unfortunately, that's a bad time for this to happen because we're hitting some pretty difficult stuff. So again, I will leave this first part optional for you to write down. But if you are like me, if you were fairly tired yesterday, if you think back to yesterday and you go, I had no idea what happened, probably should write this down. We're going to give you like a 3-minute summary of what we covered yesterday. Now, it's still going to seem fairly confusing because what we're doing right now is talking about stuff in very abstract terms. We can't go through a concrete example until we lay the whole foundation. So we're going to finish doing that today. We might hit an example today. Again, I promise. Once we hit an example, it's going to, and you get through the process, it's going to be easier. But for now, let's summarize yesterday in like 5 minutes. So the big idea I want you thinking about is I brought in that new coin, right? I forgot the coin that someone gave me. I bring in this coin. We're flipping this coin. Is the coin fair? That's what we're thinking about. And what we established yesterday, the first thing we talked about in hypothesis testing was this thing called the null and the alternate hypothesis. The null and the alternate hypothesis. And what the null hypothesis was this idea that we, unlike in chapter 9, where we're estimating some population value, whether it be the mean or the probability of success, in chapter 10, we don't know the population value like we did in chapter 9, but instead of estimating it, we're going to have a traditionally held value, and we're going to see if there's enough evidence to retain that value or go with a different one. Okay, we're not estimating the population value. We're making a decision about a traditionally held value. So the null hypothesis, if you think about the coin example, would be H sub 0, or symbol for the null hypothesis, that our population probability of success is 0.5. Okay, if we're thinking about this coin example, you assume that the coin I'm flipping is fair. What's a fair coin? 50% chance of heads, 50% chance of tails. The alternate hypothesis is the opposite. It says, while we have this traditionally held value, our data may be saying something a little bit different. So maybe we're saying, hey, you know what? I don't think that coin is fair, right? Especially if we have sample data like I flipped that coin 100 times and 80 out of 100 times it lands on heads. Your brain probably goes, wait, that coin might not be fair. If I got, say, 80 out of 100 heads, you're probably going to say, hey, I think the probability of it landing on heads is greater than 0.5. Okay, and that was the first idea we talked about yesterday. We have a traditionally held value. That's our null hypothesis. It's always going to be an equal to symbol. And then we have an alternate hypothesis, something juxtaposed with what we traditionally believe to be true. And the idea with hypothesis testing is we're going to use some sample data to make a decision about whether we reject this null hypothesis in favor of the alternate, or if we fail to reject this because we don't have enough evidence for the alternate. Again, think of a court case, right? We're seeing if there's enough evidence, okay? And so how are we going to go about this? Well, the image you can imagine is, let's say this is my population. We are assuming the null hypothesis is true. When you hypothesis test, the null is always assumed to be true. We are innocent until proven guilty. So we will assume the coin is fair. And what we're going to do is, if this is all the times I flip this new coin, we're going to take samples out of it, right? And let's say I flip that coin, giving 100 times, giving me a sample probability of 47 out of 100. And I could do this again, right? And maybe I get 52 out of 100. And these are examples of samples that wouldn't be alarming, where you're probably going, there's not really evidence here. Even though these values, these sample values, don't equal the population value, right? we'd expect this to happen with a fair coin. Where we start to get a little concerned and maybe question that null hypothesis is when we get a sample value that doesn't really make sense. I flip a coin 100 times and we get 80 heads. So how do we actually test this? Well, the idea goes back to some stuff we talked about in chapter 8 and 9. What we know is that if I have a population parameter and if I have sample values, those sample values can make a distribution. And that happens when we're working with sample probabilities or sample means. It doesn't matter. We looked at this in chapter 8, right? I can not only look at the distribution of all the fish in the pond, but I can look at 100 sample means and they'll make a normal distribution as well. And what the idea is going to be is to test this, we're going to look at this distribution of sample proportions. Again, to make this a little more clear, we know that for our distribution of sample proportions, your population value will be right in the middle, again, because we're assuming this guy is true. These values would all sit in here, right? This guy's going to be somewhere around here, this guy around here, this guy's going to be probably out here. And what we're going to do and what we'll learn more about today is we have something called the level of significance. And we talked about that with error. And so what we said is we have this null and this alternate hypothesis, and we're going to make a decision. Which one are we going to go with? Well, the way we make that call is we look at this distribution of all the possible sample probabilities, and we take the level of significance and we set some sort of cutoff region. It's going to be called the critical region. And we set this region and we say, out here, if I have a sample value fall out here, it's not very likely to happen. This goes back to the idea that area under a normal curve is equal to probability, right? It's not very likely that a sample proportion falls in this region. It's much more likely it falls in the center. And so what we're saying is if my data value would fall in this region, we will reject the null. We set a cutoff region, we look at our sample data. If our sample data falls in that region, we reject the null. If it would not fall in the cutoff region, we will fail to reject the null. And we spent a lot of time on this last concept the other day, but the final concept would be, if this is how we're making our decision, setting a cutoff region on our sampling distribution, and saying, here's our choice, we either reject the null if it's here, we fail to reject it if it's here. We do this with the understanding that we might make a mistake. Now, it's not likely to make a mistake, but we could mess up. If I am saying any value in here, I'm rejecting the null, that's a good choice most of the time, but sometimes there's a small chance I could end up rejecting the null when I shouldn't have. That's a type 1 error. We also talked about the idea of a type 2 error. We don't reject the null when we should have. So the big idea is we have some traditionally held value. We have some idea juxtaposed with it. We're going to test it by looking at a distribution of sampling probabilities or sample means. We're going to set a cutoff region. And if our data value falls in the cutoff region, we'll reject the null. If it doesn't fall in the cutoff region, we will fail to reject the null. With the understanding that we could make an error in doing this, but it's not very likely. Okay, that's the big idea from yesterday. Again, if any of those concepts you're like, man, I'm still not getting it, even after today's lesson, let me know and we'll talk, or we can meet and we can talk more about it. So now we're going to pick up where we left off yesterday, which I believe was, I believe we did this example where we interpreted a type 1 and type 2 error for the miles per gallon example. Okay, let's pick up and do another example. We'll do it with the ball bearing example. Remember for the ball bearing example, we said our null hypothesis was that the average diameter of the ball bearing was 6 millimeters. Okay, these ball bearings this company is producing have an average of 6 millimeters. It's the traditionally held value. It's the standard they need to be. What we're running a hypothesis test to see is to see if they actually are coming out at 6 millimeters. We'll look at some sample data and say, hey, can we go with our null hypothesis that these ball bearings are 6 millimeters, or is the evidence saying, hey, they're actually the average ball bearing diameter isn't 6 millimeters? And so given that ball bearing example, let's suppose the manufacturer requires a 1% level of significance. So alpha is 0.01. We want to describe a type 1 error, its probability, and its consequence. Well, thinking back to errors, the idea is with a level of significance that if we have this distribution of sample sizes or sample averages for ball bearings, and at the middle of it is our null hypothesis, what we assume to be true, if we're testing it at a 1% level of significance, that means the extreme 1% is going to be our cutoff region. That means in those extreme ends, if it's 1%, 0.5 will be here, and 0.5 will be here. If we get a sample data point and it falls beyond either extreme, we will reject that null hypothesis. Okay? So describing a type 1 error, well, what would a type 1 error be? Again, this goes back to a type 1 error is when we reject the null when we should not have. Type 1 error, we reject the null when we should not have. What does that mean in the context of our problem? We would say that the average diameter of a ball bearing is not 6 millimeters when it actually is. If you're looking at the picture, we have a data value fall in one of these extreme regions. We reject the null because it fell in one of the extreme regions, but it turns out that the null was actually true. This was just an extreme circumstance. We got an extreme data point. Our data said reject the null, but in all reality, we should not have. Okay, that would be a type 1 error. What's the probability of this type 1 error? Remember, the probability of a type 1 error equals the level of significance. So if we're operating under a level of significance of 0.01, what's the probability that we reject the null when we shouldn't have? 1%. Again, that goes back to the idea that this curve represents all the potential samples that we could draw, the middle of it being at 6. We said we're going to reject the null if our sample data value falls in either extreme. And that's a good choice because there's only a 1% chance it falls in that extreme. But again, while that's a good choice, we're still saying there's a 1% chance that, hey, our data value could fall there and the mean could actually be 6. So a type 1 error, we reject the null when we should not have. The average diameter, practically that means the average diameter of a ball bearing, we would say, is not 6 millimeters when it actually is. And the probability of that occurring equals the level of significance. What would a type 2 error be? Well, type 2 error is the opposite. If type 1 error is rejecting the null when we should not have, a type 2 error is when we fail to reject the null when the null is actually false. A type 2 error is failing to reject the null when the null is false. What is that in the context of this problem? Well, that's saying, we would say the average diameter of the ball bearing is 6 millimeters when it actually isn't. We would falsely say, hey, we're okay with that null hypothesis. There isn't enough evidence to reject it, when in reality we should have. The probability, remember, for a type 2 error is beta. Again, we're not going to get into specifics about where beta comes in. It's beyond our class and what you all need to know. Again, whether you're a stats person or not, whether this is confusing for you or not, here, the big idea you need to walk away with, because pretty much after this, we're going to be not ignoring error, but kind of setting it to the side, is the idea that when we're making a call with our data, when we are making a decision, we have to understand that while it's unlikely, we could be making the wrong decision. It's why ultimately your answers will always include this level of significance. You're saying, here's my answer under the understanding that this amount of error can happen. Again, I know some of you are still writing, so I'll give you a few minutes to finish that up before we move on. At this point, again, I remember I said there were 3 parts to 10.1 to laying this foundation. We've finished part 2. What do you have? Again, I'll leave this up to you whether you want to write down the summary or not. We did it for part 1. What's your summary for part 2? There are 2 types of error. When we make the call, we're rejecting the null or we fail to reject it, we do it with an understanding that our call could be wrong. The first way we can mess up is we reject the null when it's actually true. That's a type 1 error. That's what we're going to focus mostly on. The probability of this is alpha, and no, alpha is also called the level of significance. The third way we described alpha was it's that critical area. In the coin example, if my level of significance is 0.05, if I'm rejecting the null, my sample data falls in the top 5% of that normal curve. That's the critical region, that's the level of significance. But since I'm rejecting the null in that top 5%, I'm doing that with the understanding that theoretically a data value could fall. There's a 5% chance that it does fall there and still meets the criteria of the null being true. The other type of error we talked about is a type 2 error. We'll focus less on this. This is when we fail to reject the null when it's actually false. We say there's not enough evidence, we're going with the null. Turns out the null isn't true. Probability of this happening is beta. And again, 1 minus beta is known as the power of the test. We're not going to talk explicitly or a ton about the power. And if you take future stats classes, that'll be a concept they may hit a little more. So the big idea, we make calls. That's what we're doing. We're not estimating. We're making decisions. But in life, when you make a decision, sometimes you make the wrong call. For us, these are the probabilities of that happening. We'll focus on this one. Okay, the good news is part 3, as you will finish up writing down, I know some of you are writing the summary. The good news is, well, part 2 of 10.1 is incredibly bulky. Air is difficult to talk about, difficult to comprehend. Part 3 is a lot more like part 1, where we talked about the null and the alternate hypothesis. You'll find part 3 pretty straightforward. So what's part 3 of our foundation for hypothesis testing? Well, we've kind of already touched on it, but we're going to provide explicit terms and definitions to it. So if X bar is significantly different from the null hypothesis, you will reject the null. How are we making our decision? What are we physically doing? If X bar is significantly different from the null hypothesis, we will reject the null. What do I mean by that? Well, your null hypothesis, if you haven't picked it up yet, let's go back to the coin example. Your null hypothesis, if this is the distribution of all your potential sample proportions, all the potential different ways that I could flip a coin 100 times and get how many heads. If you haven't figured it out, your null hypothesis is always the middle of our sampling distribution because we're assuming that null hypothesis is true. So what do we mean if X bar is significantly different? We will reject the null. Well, depending on where that sample probability falls, and depending on where we set that cutoff region, if that sample probability falls in here, we're going to reject the null. We'd say that is significantly different. If it doesn't fall in that cutoff region, we will say it's not significantly different. We'll fail to reject the null. Now, please understand that depending on what our population value is, here I'm working with P, the probability of success, that determines what this guy is. So this guy could also be P hat. It just depends on the parameter we're working with. If we're working with population mean, we're going to work with X bar. If we work with population probability, we work with P hat. The values of X bar. So if X bar is significantly different, we're rejecting it. Well, what are the values of X bar that are sufficiently off? That is called the critical region. We're saying, okay, Mr. Carter, X bar, if it's so far off of your population mean, your null hypothesis, your population probability of success, we're going to reject it. Cool. What do we call that area? That's the critical region. That's this guy right here. And again, as we've established before, the area of that critical region is alpha. Your level of significance determines this region, how big it is. So the whole idea, again, we've talked about it several times now. Our null hypothesis sits right in the middle of this sampling distribution. We're going to look at a specific sample and see where it falls. If it falls far enough away, we're rejecting that null. What's that area called if we're far enough away? The critical region. How do we find the critical region? Well, it's alpha. It's our level of significance. There are three potential critical regions. There's left-tailed, right-tailed, and two-tailed. So we just established what the critical region is. It's the area on the curve that we say, data value's too extreme, rejecting the null. And there are three potential critical regions we can have. There is a left-tailed region, okay? The way we will recognize that is by looking at our alternate hypothesis. If our alternate hypothesis is a less than, then we will have a left tail. So what you can imagine here is your means in the middle. This is a distribution of all your potential sample means. If our alternate hypothesis, think of the miles per gallon example, right? Our null hypothesis, hey, we're advertising that the subcompact cars get 47 miles per gallon. And we go, wait, we think it's actually lower. Your critical region will be over here. That's called a left-tailed test. It's on the left side. Again, this is all based on your alternate hypothesis. If it's a less than, it's going to be on the left side. At this point, you can guess what's going to happen if our alternate hypothesis is a greater than, like the coin example. Right? We think the coin isn't fair. We think the probability of it landing on heads is higher than 0.5. And you're going to run a right-tailed test. So on your distribution of sample means, that critical region where we reject the null will be the top right-hand portion of your sampling distribution. If, like the ball bearing example, you say, we don't really have a specific, we think it's over, we think the null hypothesis is too high, or we think the null hypothesis is too low, we just think it may be wrong, well, then you're going to have a two-tailed. Your null hypothesis in the middle, because we're assuming it's true, and you'll have a critical region on either side. And this should make sense, right? If we're running a not equal to, if our data value is too high or too low, it could cause us to reject the null. If we think about the coin example, and you don't care about too many heads, you just care about the coin being purely fair, well, you're going to be surprised not only if I get 80 heads, but also if I only get 20 heads. Either way, you're probably thinking, hey, that coin's not fair. You're going to have extremes on either side where you go, hey, I'm going to reject the null. Again, what you need to walk away with knowing is that the alternate hypothesis is what determines where the critical region is. When we establish this guy, it will determine where that critical cutoff area is. So we reached the end of 10.1. Again, I will leave this up to you. If you want to listen to the overall summary, that's fine. If you want to write it down, be my guest. Here's the big idea. Number one, we're always going to establish a null hypothesis and an alternate. The null, what we know, the traditionally held value. The alternate, that's replacing what we know. A new idea, right? The coin is assumed to be fair, but it might not be. the level of significance, which is going to determine the size of our cutoff region, and is also equally the probability of a type 1 error, is used as the symbol alpha. Okay, incredibly important for us. We also talked about this idea of power, which has the probability 1 minus beta. Comes from the idea that the probability of a type 2 error is beta. Remember, a type 1 error, we reject the null when we shouldn't have. The type 2 error, we don't reject the null when we should have. Finally, the alternate hypothesis is going to determine what the critical region will be. If our alternate hypothesis is a less than, it'll be a left-tailed. If it's a greater than, right-tailed. And if it's just a not equal to, it'll be a two-tailed. So obviously, very bulky, very abstract. What I think would be a good idea, I want you to, it's 8:35, let's take till 8:40 and take a break, okay? You can be on your phones, you can talk to other people, do what you want. What we're gonna do after this is we're gonna start 10.2. Physically, how do we run the hypothesis test now that we have a basis? But for now, take a break. You can draw, listen to music, talk to other people, play on your phone, do what you want. Take a break. If you need to get up, go to the restroom, take a walk because you're sleepy, be my guest. Absolutely.
Why? Is that what you're doing? Your mom's mom? Really? I don't know. They told me mom. She doesn't like me. Who, you're talking about? She's like, yeah, but you're not. She's like, she can't go back. She doesn't. That's hilarious. Wait, so you were. Is that true? I'm like tired. I saw it. I can't
Okay, let's bring it back. So again, if you're looking to organize your notes, what we're doing now is we're starting 10.2. We have finished 10.1, which is an intro to hypothesis testing. What's the idea of it? What are we going to be doing? 10.2, we get more into the executing it. Okay? So how are we going to do it? Well, it's an 8-step process. Now, if you read about this process in your book, if you look at a different textbook, if you go and take a stats class at Owens or college or something else, this is going to be a little bit different everywhere you go. Maybe they would combine it into 4 steps. Maybe they expand it into 12. To me, through all the stats classes I've been through all the textbooks I've read, all the videos I've watched, to me, this is the best way to describe it in these 8 steps. Okay? So the process, and again, in your notes, I would box it, I would star it, I would check it. We're going to edit it a little bit in later sections, but this is pretty much the process for any hypothesis test. Doesn't matter if we're doing the population mean, doesn't matter if we're doing the population probability, this is the process we're going to follow. We are always going to start by identifying known information about the population and sampling distribution. You might not know what that means, but we've done it plenty of times before. This is simply reading the word problem and pulling out the important info. What is the population parameter that we're trying to study? What's the sample size? What's the standard deviation? Do we know the population standard deviation? Do we know the sample standard deviation? We've seen many times that I keep drawing this sampling distribution on the board, the distribution of all those sample means or all those sample probabilities. What's the mean of that? What's the middle of it? What's the standard deviation of it? That's the known information we're going to identify. Step 2, we're going to write our null and alternate hypothesis. Just like in the scientific method, you always are going to start by establishing a hypothesis. What's our traditionally held value? And what do we think might be the alternate? Step 3, we're going to identify the level of significance and potential errors. The level of significance helps us determine where that cutoff area is going to be, so that's important to identify. And with that, we must acknowledge that in our decision making, we could mess up. And what would that error look like, and what's the probability of it happening? Number 4, we're going to identify the type of test. What do we mean by the type of test? Is it left-tailed, is it right-tailed, or is it two-tailed? Where is that critical region? 5, we're going to identify the critical region and the critical value. This is where we're going to physically get into calculating. We'll use our calculators. I'll show you the process for finding the physical boundary of from here on is where we're going to reject the null, and from here back, we will not reject the null. Step 6, we're going to find our test statistic. This is our sample data. Once we say, here's the cutoff point, Now we're actually going to look at our sample data and see, well, does it fall beyond the cutoff point or not? Number 7, we're going to analyze the results. That's going to be us saying, did we reject the null or did we fail to reject the null? And then 8, we're going to write the conclusion. That's like interpreting it in the context of the problem with confidence intervals. Okay, we rejected the null. What does that mean in the context of the problem? Okay, we failed to reject the null. Again, what does that mean in the context of the problem? This is the process you're going to follow every time. And this is the process I want you doing every time. Okay, your book, again, articulates it a little bit differently. So when you go to do the homework for 10-2, and it says all these different steps, I want you doing these. Okay? You will hit the criteria that they are asking for by doing these 8 steps. And I think they're a little clearer than what the book describes. So again, I don't care if you need to box it. I don't care if you need to write next to it important. I don't care if you need to put a highlighter, circle around it. Do whatever you need to do. These are the steps for hypothesis testing, and they're not going to change too much. We might add a couple here and there, but this is what we're going to stick with. Okay. Again, this is just a reminder. How are we making our call? It's going to be by seeing if the statistic is far enough away. I'm not going to make you write that down again. You've already written it in your 10-1 notes. This is just a reminder. The big idea here is our sample data. Does it fall in that critical region or not? Is it far enough away from the null hypothesis? So how are we going to find the critical region and critical values when the parameter is a mean? Now we're going to hone in on 10-2. 10-2 is going to focus on the mean and large samples. Okay? That means we're going to be working with mu, and our sample size is going to be bigger than 30. If you remember back to chapter 8, by the central limit theorem, your sampling distribution, your distribution of sample means, your X-bar distribution, is normal when this is true. This is incredibly important for us because it allows us to run the hypothesis test. Again, in later sections, we'll work with maybe the population probability. We'll learn how to work with small sample sizes, which again, if you remember, that means t distributions. But for now, we're working with large samples, and that sample size is bigger than 30. So what are we going to be doing? Well, we're going to have a null hypothesis. That mu is equal to some value. Let's call it 50. And let's say we have an alternate hypothesis. Mu is greater than 50. Again, we've said it a million times. How do we run the hypothesis test? Well, what we're going to do is we're going to look at the sampling distribution. Right? We're going to look at the distribution of all your potential samples. Okay? Let's say they're samples of size 100. Right? We're looking at samples of size 100. So all the potential samples of size 100, we look at the sample mean for each sample of size 100, and it makes this distribution. What's at the middle of that distribution? Your null hypothesis, because we're assuming it to be true. What we would do at this point is then identify some standard deviation, right? How much variance do we expect? And then based on our significance level, we have this cutoff region. Now what we've said is alpha is always going to be 0.05 or 0.01. Okay? In other words, if I'm running a right-tailed test here, right? If I'm saying, you know what, if my data value, if my sample data value falls in the top 5% of sample data values, I'm going to reject the null. Here we're rejecting the null. Our data value would fall here, we're failing to reject the null. The question becomes, where is this cutoff point? How do I find this guy? Okay? If my mean is 50, how do I find the cutoff point? Well, because the sample size is greater than or equal to 30, the X bar distribution is normal. Okay, that's your central limit theorem. Why is this important? Because we have found already in previous chapters, how do we find cutoff points on graphs? We do it by finding critical values. In other words, we look at the standard normal curve. So if this is normal, what I can do is I can look at my standard normal curve, and I can say, okay, I have a normal curve, and the top 5% is going to be my cutoff region. Where's the cutoff point? Well, how did we find that in the past? We have an area on a normal curve. How do we find the cutoff point? We use inverse norm. So in general, how are you going to find your cutoff point? Well, since our distribution of sample means is normal, we can look at the standard normal curve, and we'll type our area left, and we work with the standard normal curve because we know the mean and the standard deviation. Mean is 0, standard deviation is 1. This is how we're going to find what's called the critical value. The critical value is the cutoff point. Right? If the idea is that if a data value falls in the top 5% of my data, I'm rejecting the null, well, we got to know where that top 5% starts. Right? We can't compare our data value if we don't know what this green line is. So how do we identify where the top 5% starts? Well, because this is a normal curve, we can look at the standard normal curve, which is how we compare different data sets, and say, how many standard deviations away do I need to go from the mean so that from there on, there's 5% of my data. Again, we'll do different examples of this. If you were to solve this specific problem, how would you find your cutoff point? Well, my data, I'm looking for the point such that 5% of the data lies to the right of it. How much area left is that? 0.95. So I would theoretically do in a calculator, inverse norm, 0.95, 0, and 1. What that is going to give me is on the standard normal curve, which remember has a mean of 0 and standard deviation of 1, it's going to give me the data value such that 5% of the data lies beyond it. Now here's what you might be thinking. You might be sitting here and going, okay, cool. On this standard normal curve, we know the cutoff point where 5% of the data lies beyond it. But that doesn't help us when our data value is falling on this curve. Right? Maybe my data value, my specific sample mean falls here. Or maybe it falls here. Or maybe it falls here. Either way, my cutoff point, I didn't find it on my sampling distribution. I found it on my standard normal curve. So how do we get this guy from here to here? How do I transfer my specific data value to the standard normal curve where I know where the cutoff point is? Well, you use this formula. Z equals x bar minus your mean over your standard deviation divided by the square root of the sample size. What that's going to do is that's going to transfer your specific data value to the standard normal curve. That takes those red lines I drew and say, where do they fall on the standard normal curve? Again, why are we doing this? Because on the standard normal curve, I know how to find my cutoff point. I don't know how to do that, or we're not going to do that on our specific X distribution of sample means. So because the sample size is bigger than 30, our distribution of sample means is normal. We have a significance level that says if my data point falls in the top 5% of my data, reject the null. Otherwise, don't. Well, how do we find the point where that top 5% starts? Transfer your data to the standard normal curve, use inverse norm. How do we find then where our data value falls in relation to that? This formula right here. That formula takes this red line and transfers it to this graph, wherever it may fall. So let's finally look at an example. Again, if you're anything like me, this last amount of time has been brutal because you like to learn through examples. Okay, so let's do this together. You're going to notice that these numbers I have down here are the exact same processes you already wrote down. It's the 8 steps. So suppose a biologist studies rare turtles. Please do not write this example down. You're just going to start by writing down the important info. One of the main ways to determine if a turtle nest is inhabited by rare turtles is to measure the length of the eggs. Rare turtles are known to have a population mean length of their eggs of 7.5 centimeters with a standard deviation of 1.5 centimeters. Common turtle species lay eggs that are larger in size. So in a commonly known turtle breeding spot, a biologist recognizes a nesting pattern identical to that of most rare turtles. However, the average length of the 36 sample eggs she found was 7.74 centimeters. Run a hypothesis test with alpha equals 0.01 to see if the sample eggs are indeed from rare turtles. Okay? To summarize that, we know that we're operating under the understanding that turtle eggs, rare turtle eggs, have an average length of 7.5. She finds this collection of turtle eggs that she thinks, based on the nesting pattern, might be rare turtle eggs. But she's concerned because of how big the length of the sample is. What she's going to run a hypothesis test to see is this too big? It's like the coin example. Am I getting too many heads to the point where we question, hey, maybe that's not a fair coin? She's saying, is the length too big where we go, you know what, despite the nesting pattern, I don't think these are rare turtle eggs. That's the call we're going to be making. So let's start by identifying the important information. Well, the first thing we see is there is a sample size of 36, right? The sample size will become important as we work through this. This is also incredibly important because it means we're working with a large sample, right? That's going to mean our distribution of sample means is normal. Again, that sample size is bigger than 30, important to note. We were also given a population mean of 7.5 centimeters. Okay, this was the average length of all rare turtle eggs, are this size, with a standard deviation of 1.5. Again, a little thing to note, we may not always know the population standard deviation? We do in this case. If we don't, we can use S instead, the sample standard deviation. Again, if we're working with a large sample size. Again, that's a concept we talked about in chapter 9. Other important pieces of data to know. Our sample mean was 7.74. That was the average length of those 36 eggs she specifically found. Right? This is the average of all rare turtle eggs. This is the average length of the 36 that she thinks might be rare turtle eggs. Again, you've noticed that we're working with the X-bar distribution. We haven't done this since chapter 8. But what's the mean of that X-bar distribution? Well, again, remember it's the same as your population mean. It's 7.5. That distribution of sample means, all the potential sample means of size 36 has the same mean as your population mean. And what would your sample standard deviation, or what would your standard deviation of that distribution of sample means be? Well, again, remember that's your population standard deviation divided by the square root of the sample size. And to save you some time, that will come out to be 0.25. This is the important info we've gathered. And again, for problems similar to these, by that I mean we have a population mean and a large sample size. This is the info we want to gather. So from there, let's identify our null and our alternate hypothesis. Again, if you feel like you can already do this, go ahead. If not, stick with me. What's our null hypothesis? Well, it has looked at these eggs, and based on the nesting pattern, assuming they are rare turtle eggs. So our null hypothesis is that the length of all average the average length of all rare turtle eggs is 7.5. We're assuming those eggs are from a rare turtle egg nest. Our alternate is that our population mean is larger than 7.5. What this alludes to is that all other turtle species lay eggs larger than that have an average length of larger than 7.5 centimeters. So that would be our alternate hypothesis. Our traditionally accepted value for rare turtle eggs, 7.5. Common turtle eggs lay eggs bigger than that. We are concerned, while we assume that our eggs are rare turtle eggs, we're concerned that they might be too large. Identify the level of significance and potential errors. Step 3. Well, we have a level of significance of 0.01. What that means is that we're going to be looking at the extreme 1%. If our data value falls in the top 1%, we will reject the null. If it doesn't, we will fail to reject the null. What are potential errors? Well, again, we acknowledge what a type 1 error would be. That would be we reject the null when we should not have. That would mean we say, hey, you know what? The eggs are not rare turtle eggs. When they actually are. The eggs are not rare turtle eggs when they actually are. We reject the null. What would a type 2 error be? Well, it's the opposite. That's when we fail to reject the null when we should have. That means we fail to reject, or that means the eggs, we say the eggs are rare when they actually aren't. Eggs are not rare is our conclusion, or that we conclude that the eggs are rare, we would go with the null hypothesis, when in reality they are not. We should have rejected the null. We should have said they were common. Again, the probability of this is beta. But more importantly, what's the probability of this type 1 error? Alpha. There's a 1% chance that we make that error. And at this point, once you have that written down, we will stop there for today.